All right, today we're going to build a machine. Not with gears and metal, though. We're going to build it with ideas. It's the statistical engine that powers pretty much everything, from the stock market to how we discover new medicines. We're going to assemble this thing piece by piece, starting with the most basic, fundamental component, the random variable.
So get this, what if I told you that the number of views on a YouTube video, the weather tomorrow, even the roll of a die are all governed by the exact same fundamental concept? These aren't some kind of mysterious forces, they're just mathematical tools called random variables, and by the time we're done here, you're going to understand exactly how they work.
So let's start at the very beginning, with the absolute foundation. What in the world is a random variable? Just think of it as the first, most crucial gear in our whole statistical machine. At its heart, a random variable is just a rule. It's a function that takes the outcome of some random event, like flipping a coin, and it just assigns a number to it. For a coin toss, we could say heads is 1 and tails is 0. Simple. For a die roll, well, the outcomes are already numbers, 1, 2, 3, 4, 5, or 6. We're basically just translating real-world chance into the language of math.
Now, these variables come in two main flavors, discrete and continuous. And the difference is actually really simple. Can you count the possible outcomes, or do you have to measure them?
Discrete random variables are the countable ones. You can actually list out all the possible outcomes, even if that list goes on forever. Think about the number of heads you get in 3 coin flips. You could get 0, 1, 2, or 3. That's it. There's nothing in between. Same goes for a die roll, or say the number of customers who walk into a store in an hour. They are distinct, separate values.
So how do we actually map out the probabilities for these countable outcomes? Well, we use something called a probability mass function, or PMF for short. It gives us the exact probability for each specific result. So for a fair die, the PMF just assigns an equal probability, 1/6, to rolling a 1, a 2, and so on, which you can see right here as these nice clean bars.
Okay, time for a quick check-in, just to make sure this is all clicking. Let's say we're looking at the amount of water your household uses in a day. Is that a discrete variable or is it continuous? Just think about it for a second.
It's continuous. And why is that? Well, you can't really count water usage in these neat little steps, right? It could be 150 liters, or 150.5, or 150.51. It can take on literally any value within a range. The key difference is right here. You have to measure it, you don't count it. And this leads us to how we handle continuous variables. Think about it. What's the probability of someone being exactly 180.000 centimeters tall? I mean, with an infinite number of decimal places, the chance is basically 0. So instead, we use what's called a probability density function, or PDF. We stop asking about a single point and we start asking about a range. The probability of someone being, say, between 175 and 185 centimeters tall is simply the area under this curve between those 2 points.
Awesome! So now we know what random variables are. But how do we describe them? We're going to add 2 more really important parts to our machine that let us measure their core properties, their center, and their spread. First up, we've got the expected value, which we write as E of x. This is just the long-term average value you'd expect to see if you ran an experiment over and over and over again. For a discrete variable, you calculate it by taking each possible outcome, multiplying it by its probability, and then adding all those results up. It's basically a weighted average, where the outcomes that are more likely get more weight.
Let's make this super concrete with our die roll example. We've got 6 outcomes, right? Each one has a probability of 1/6. We just plug them into our formula. We add up 1 through 6 and multiply that whole sum by 1/6. The total is 21 times 1/6, which gives us 3.5.
I know what you're thinking. You can't actually roll a 3.5 on a die, and you're right. So what on earth does this number mean? Well, it's the theoretical balancing point. Imagine all the outcomes, 1, 2, 3, 4, 5, and 6, sitting on a seesaw. The expected value is the exact spot where that seesaw would balance perfectly. It's the center of mass for the entire probability distribution.
All right, next up, variance. If the expected value is the center, then variance measures the spread. You could think of it as how wobbly the outcomes are. A really small variance means the results are all tightly clustered and pretty predictable. A huge variance means they're all over the map. The formula might look a little scary, but all it's really doing is calculating the average squared distance of each outcome from that center point, the mean.
So why should you care about this? Let's imagine you have two machines filling up soda bottles. Machine A has a variance of 4. Machine B has a variance of 25. Which one would you rather have in your factory? Which one is more consistent? Machine A, for sure, absolutely. Its lower variance means the amount of soda it puts in each bottle is much more tightly packed around the average. Machine B is way less predictable. You're going to get some bottles that are overfilled and some that are underfilled. In finance, a lower variance means lower risk. In manufacturing, it means higher quality. So yeah, it's a really crucial idea for managing uncertainty.
Okay, so it turns out that a lot of random things in the real world actually follow these really predictable patterns or blueprints. So let's take a quick little tour of some of the most common statistical distributions out there.
There are a ton of these blueprints. Some of the big ones you'll always see are the binomial, which is for counting successes, the Poisson for counting events over a period of time, and of course the famous normal distribution, the bell curve. To really see how these work, let's zoom in on one of the most useful ones, the binomial distribution.
The binomial distribution answers a very specific question. If I have a set number of trials, what's the probability I get a specific number of successes? And this formula tells us exactly how to figure that out. It's really just multiplying three things together. First, the number of ways you can arrange the successes you want. Second, the probability of getting those successes. And third, the probability of all the failures. Let's actually solve one. Imagine a basketball player who makes 60% of their free throws. If they take 5 shots, what's the probability they make exactly 3 of them? Okay, in our formula, n, the number of trials, is 5. P, the probability of success, is 0.6, and k, the number of successes we're looking for, is 3. We just plug those numbers in. 5 choose 3 is 10. We multiply that by 0.6 to the power of 3 and 0.4 squared, and we get a final answer of about 0.3456, so there's a 34.56% chance.
You know, so far we've been living in this kind of theoretical world. But in real life, things are messy. We almost never know the true properties of an entire population. I mean, you can't poll every single voter or test every single car off the assembly line. So what do? We do the next best thing. We take a sample. This next part of our machine is all about how we can use a small group to understand the whole.
And it turns out there are some really smart ways to collect these samples. For instance, in simple random sampling, everybody has an equal chance of getting picked. But in stratified sampling, we make sure we get a good representation from different groups, like different age brackets. Each of these methods is just a different tool designed for a specific job.
Okay, now this next part is a little bit of a brain bender, but it is so important, so stick with me. Imagine we took every single possible sample of, say, 30 people from a population. For each one of those samples, we calculate the average, and then we plot all of those averages on a graph. We'd get a brand new distribution. This is called the sampling distribution of the mean. And here's the crazy part. The sample mean itself acts like a random variable. It has its own mean and its own variance.
And the standard deviation of this special distribution, well, it's so important it gets its own name, the standard error. It tells us exactly how much we can expect our sample averages to bounce around the true population average. And just look at that formula. Do you see n, the sample size, sitting there in the denominator? That is a huge deal. And that formula tells us something incredibly powerful. As your sample size n gets bigger, the standard error gets smaller. And what does that mean? It means a larger sample gives you a much more precise estimate of the real population mean. The wobble in your measurement shrinks, and your confidence in the result just skyrockets. Let's lock this in with a quick example. Let's say we know the standard deviation of IQ scores in the population is 12. If we take a random sample of 36 people, what's the standard error of the mean for that sample? We just plug the numbers straight in. 12 divided by the square root of 36. That's just 12 divided by 6, which gives us a standard error of 2. It's as simple as that. Okay, we've built all the pieces. We have random variables, we have our distributions, and we understand sampling. Now it's time to flip the master switch that connects everything together. This is the Central Limit Theorem, and honestly, it's one of the most beautiful and powerful ideas in all of mathematics. Okay, listen closely, because this is incredible. The Central Limit Theorem says this. I don't care what your original population's distribution looks like. It could be skewed, it could be flat, it could be a total random mess. It does not matter. If you take large enough samples, and the rule of thumb is usually 30 or more, the distribution of the sample means will always start to look like a normal distribution. That perfect bell curve. It's like magic. Order just appears out of chaos. And why is that so incredibly powerful?
because we know everything about the normal distribution. The CLT lets us take our sample mean, that's x bar, and compare it to the true population mean, that's mu, using this z formula. It basically just tells us how many standard errors away our sample result is, which then lets us figure out how likely or unlikely our result is. This is the engine that drives almost all of modern statistics.
So let's just take a step back and look at the machine we've built. We started with the basic gears, random variables that turn chance into numbers. Then we added some gauges to measure them, expected value for the center and variance for the spread. We learned how sampling is our probe, our way of looking into the world. And finally, the Central Limit Theorem is the master switch that makes the entire machine reliable, telling us that our results will almost always follow a predictable, normal pattern.
And there you have it. That's the fundamental blueprint for the engine of statistics. From a single random number all the way to a theorem that literally finds order in chaos, you now have the tools to understand how we make sense of a really uncertain world. So the next time you see a poll, a scientific study, or a financial model, you'll know about the elegant, powerful machine that's working right behind the scenes. If this helped you out, share it with someone else. Thanks for watching.